So we spent the last few videos looking at what we call the geometric distribution, and you can tell I'm still a little stuck on the geometric distribution here. We're looking at something a little bit different this time. The geometric distribution, we had repeated trials until we got our first success and then stopped, and we recorded how many trials it took to get the first success. That was the thing we cared about. Here we're looking at something a little different. We're looking at a fixed number of trials. So in this particular example here, I flipped a coin 6 times and recorded how many heads, so how many successes there were in the trial. And I did that 20 times. And I got 1 head out of 6 twice, I got 2 heads out of 6 5 times, etc., etc. Recorded them there, and then made a histogram. So this shows that out of the 20 times that I flipped the coin 6 times, that's a total of 120 flips, I got 1 head out of 6 exactly twice, 2 head out of 6 exactly 5 times, 3 out of 6 exactly 6, 4 out of 6, etc., etc. Remember, that's experimental or empirical probability when we actually count how many times each outcome occurs, right? The outcome is the number of heads that we got. So the outcomes aren't the heads here. The outcome is the number of successes. The success is the head. The outcome is how many heads did I get out of my 6 flips. I then ran the theoretical results, what I should have gotten in the long run over time if the probability of flipping head is actually 1/2. And that's what you see in red there. Now, when you do it empirically or experimentally, I'm going to get 3 a specific number of times, like 5 or 6 or 7 or whatever. I'm not going to end up with 6.18 times. When you do it theoretically, you can end up with 6.18, and that's what the red shows there. If we were to round the reds off to the nearest whole number, we would have gotten exactly my empirical results, which actually is quite surprising. When you do something with a small number of trials like 20, you should not get exactly what the theoretical probability implies. That's actually fairly unusual that happens. So this is an example of a binomial distribution, and we use it to explain or make predictions in certain situations that fit these descriptions. We have a fixed number of trials. You're going to flip the coin 6 times. That's a fixed number of trials. Contrast that to the geometric, where we were going to flip it until we got head. Each trial has the same probability of success or failure. That's the same as we did in the geometric, right? Geometric, the probability of success or failure never changed. But here we're starting with a fixed number of trials, and we're dealing with the same probability of success each time, and those are still called Bernoulli trials. And I still haven't looked up his first name, but I believe he's still Swiss. And we care about the number of successes out of our fixed number of trials. So not how many successes does it take to get to flip ahead, how many successes did we get out of those 6 flips. Now our coin flip is easy to understand, but it is fairly limited because the probability of success and the probability of failure, heads and tails, is the same. So everything we do with a coin flip is really limited by that. In this case, it makes it look like our binomial distribution is going to be symmetric. It's not always going to be symmetric, and here's an example of that. Here I wrote in different pens, so it's a little harder to read, but number of 1s that came up in 6 rolls of a die. I rolled the die 6 times and counted how many times it came up 1. Actually, that's not true. I rolled 2 dice 3 times for a total of 6 rolls and counted the number of 1s. When I left my office in the spring, didn't bring dice with me, so I had to scrounge around and finally found this pair in, I think it was a game of Monopoly or something. So I've only got 2 dice to my name at the moment until I get back to my office. So I rolled 6 times, recorded how many of them were 1s. Boom. Did it again, recorded how many came up 1, and represented each one with a dot. And I did that 20 times, and these are the results here. That's what we've got in the histogram in black here. I believe it was 8 times I got 1, 6 times I got 0, 5 times I got 2, and only 1 time it came up with 3 1s. Now think about our expected outcome that we've talked about so many times. How many ones would you expect in 6 rolls? Well, if the probability of rolling a 1 is 1 in 6, then you'd expect 1, and that is the one that shows up the most often. 0 and 2 a little less, and not symmetric like the example with the coin. They aren't the same height as each other. You're actually more likely to get no 1s in 6 rolls than you are to get 2 1s in 6 rolls. And then, of course, we have the little tail of the graph tapering off down here. I ran the theoretical numbers again, and that's what the red are. 1 was exactly on. My 2s were a little higher than theoretical. My 0s were a little lower. So actually, as much as those bars seem wrong for being asymmetric, they should, quote unquote, should be a little more asymmetric than they actually are. Now let's look at a formula real quick here, and you'll see why we're not going to be doing this a whole bunch. The probability of rolling 2 1s in 6 rolls, the way we would calculate that, given the tools that we've been looking at so far, we would take the probability of success to the second power, because we're talking about 2 successes. We would take the probability of failure, right? The probability of success is 1 in 6 for rolling a 1. The probability of failure is 5 in 6, 1 minus 1/6, and we have 4 failures. If we've got 6 rolls, 2 of them are successes, then 4 of them are failures. So we have the probability of failure to the 4th power. And then we multiply that by, if you recognize this as the combinations formula, this is 6 choose 2 or 6 choose 4, depending on how you care to look at it. They end up being the same. So I want to run that in the calculator just for kicks. We've got 1 divided by 6 to the 2nd power times 5 divided by 6 to the 4th power, and then we're multiplying that times 6, and where do we get that from? Math probability 6C2. You'll come out same if I said 6C4, and that would be 0.2. If I multiply that times the 20 rolls that I made, it says I should have gotten 4 times I should have gotten exactly 2 1s. And that's where that red line came from. That came out exactly at 4. In actuality, I ended up with getting 2 1s 5 times out of the 20 trials that I did, or the 20 repetitions of the 6 rolls. And we'll get more into the math and how to use the calculator for this next time.